Hi, my name is Jeff Crowley from Astra. Today I'm going to talk about the Global Ultraviolet Ionosphere Thermosphere Observatory, or GUVITO. GUVITO means small GUVI or son of GUVI, because the GUVITO instrument is derived from the GUVI instrument that flew on the NASA TIME satellite. So here I've got some information to give you an overview of the GUVI instrument. So now I want to talk about the GUVI instrument that was the predecessor of GUVITO. GUVI flew on the NASA TIME satellite, and here's a picture of the scan pattern for GUVI. GUVI looks down on the limb and down on the disk of the Earth, scans up onto the limb to about 520 kilometers, then flips back and does the whole thing again. Scans across the disk up onto the limb and then flips back. It does this all the time as it's traveling in an orbit perpendicular to that scan pattern. GUVI's in a fairly high inclination orbit, so it sees the aurora very often. Here's a strip of the GUVI data from part of an orbit going over the North Pole, and you see that scan on the disk and up onto the limb, about 2,000 kilometers wide as a function of distance along the orbit. And here you see the aurora being detected by GUVI at high northern latitudes. So this is data looking down on the disk, and here we've put the different orbits side by side to map the Earth as the Earth rotates under the GUVI orbit. And you see these bright bands here close to the equator. These are called the Appleton anomalies. They have high electron density in the ionosphere, and within them you see a lot of structure caused by ionospheric irregularities, some of which would cause scintillation of GPS signals, for example. Here's a view looking at just the limb data, again side by side, superimposed on the geographic coordinates, and you see the variability of the Appleton anomalies at different longitudes on the Earth and as time goes by, and you also see the aurora at the higher latitudes here. This is on the day side. On the night side, GUVI also makes measurements on the day side, and so this is a altitude versus latitude picture, and what we've done is put vertical scans side by side along the orbit to get this picture. This is looking at the molecular nitrogen, N2, and it's the variation as a function of latitude for magnetically quiet conditions. This panel B is the similar pattern but for geomagnetic storm conditions, and you can see that there's quite some difference. This third panel shows you the difference in detail, and we can do similar observations for the atomic oxygen, for example, or for the temperature. This is now the dayside data looking down on the disk, and we've put orbits side by side for 5 days here. Time runs from right to left, and we superimpose the data on the geographic coordinates again. So during the 2 first days here, it's magnetically quiet. You see that there's a hemispheric asymmetry. The brighter red colors are in the winter hemisphere, meaning higher values of N2, and the more blue colors are in the southern hemisphere. You also see this daily variation caused by the offset of the magnetic and geographic poles. On the 3rd day there's a geomagnetic storm, and you see this red area penetrates towards the equator, and there's much bluer regions at higher latitudes during this time. In the southern hemisphere the blue regions also encroach towards the equator, and then a few hours later you get a recovery of the atmosphere and we get magnetically quiet conditions again, restoring things to normal. There's not time to go into all that GUVI can observe, but this chart tells you the 5 different wavelengths or wavelength bands that we record, the colors as we call them, and these are the different observing conditions, for example the dayside limb, the dayside disk, etc. And these are all the environmental parameters that we can derive from the GUVI data. And now I want to talk to you about some of the GUVITO design criteria. So GUVITO is going to be quite an advance over the GUVI instrument. It's going to have a smart scanning capability that's servo controlled. It's going to have a longer lifetime. It's designed for an 8-year lifetime, and it's going to be versatile in the sense that the scan can be changed during a scan. You can change the scan rate, you can change it during the orbit, and it can be commanded from the ground after the mission is launched. So this is a picture of the scan mechanism itself, and this is a picture showing you the GUVI stair-step scan that's caused by the gearbox mechanism that was used in GUVI. This is a picture corresponding, showing you the corresponding Guvito scan. You can see that it's much cleaner, much smoother, much more well controlled. And the Guvi scan takes 15 seconds. Guvito can scan in that same 15 seconds, but it can actually go much faster at about an 8-second scan if we wanted it to. But not only can it go faster, but we can also, as I said, change the scan rate during the orbit. So here's one scan rate, and then, or during the scan, and we can change that during the orbit, so that we can focus on regions of interest, special interest, or we can look at regions where the signal is perhaps not so bright. We can dwell in that region for longer to get better signal to noise ratios. This is a picture of the servo control system concept, and we've actually simulated the Guvito scanner in software to make sure that it's going to work as expected and really to demonstrate some of its capabilities. Finally, I want to talk about the mass estimate here. Guvito is going to weigh quite a bit less than Guvi. The scanning imaging spectrograph portion of Guvito will be about 20% less than Guvi, just with the different parts and losing some of the redundancy. But when we use lightweight materials for the housing and some of the other parts, we'll actually come in at 30% less massive than Guvi. So what that means is that Guvi, with the detector electronics, came in at about 12 kilograms. Guvito will come in about 9 kilograms. When you add in the data processing unit that will be required, for Guvito it's going to be about another 5 kilograms, bringing us to under 15 kilograms for the entire instrument, whereas Guvi for the entire instrument was about 25 kilograms. So now I want to talk to you about the instrument simulator that we've been working on for the Guvito instrument. We've simulated the 1356 emission and the LBH long and LBH short emissions, and these figures here show you the atomic physics that's responsible for the emission of the 1356 angstrom, and here's a list of the different mechanisms that cause it. And at the top here is the Guvi data. We're using Guvi data to actually test our simulation, and so we're attempting to simulate the Guvi data, but then we'll modify the simulator for Guvito. And here's 4 different simulations showing as a function of latitude or orbital location versus location across the scan. So this is for showing all the scans for one orbit. And in the central part here is the day side, and on either side of it are the night side. And you see that there's day side enhancement looking up on the limb, very bright, and then you also even see the enhancements from the 2 Appleton peaks on either side of the equator. These 4 simulations are with a 50% cascade contribution and 100% cascade contribution, with no LBH 1356 contribution. And then on the bottom 2 are the 50% and 100% cascade with the LBH contribution. And as we were expecting, the 50% cascade with LBH contribution is the best match with the Guvi data. I also want to mention that we used a background model of the ionosphere and thermosphere in order to do these simulations, and this was based on a time GCM simulation. We've done a similar thing with the Guvi LBH short and the Guvi LBH long, and we've compared it with our simulation, and again you can see reasonably good results. There's a little bit of fine-tuning that could be done here, but on the whole we're getting a remarkably good simulation. So in summary, I've got some conclusions here. We've got a new hardware design. It's robust. It's got an 8-year on-orbit lifetime design. We're using 2 scan mechanisms, 2 scan motors to drive the mirror, and the mass is significantly smaller than the Guvi mass. The SIS itself weighs about 9 kilograms, and we expect that with the electronics, with the detector electronics, and we expect the DPU to come in at about 5 kilograms later. The scan mechanism itself has been simulated in software, looks to be behaving well, but it's much more capable than the Guvi scan, more versatile and programmable and controllable once the instrument gets on orbit. The instrument simulator, as I mentioned, is doing a pretty good simulation of the Guvi data and will therefore give us a good estimate of how Guvito is going to perform. There's significant innovation in this instrument. We've currently focused on the scan mechanism itself, but we're also expecting to have a new detector with a higher quantum efficiency, new digital processing unit with higher speed electronics, which will also actually require less power and a smaller footprint, so we'll need much fewer spacecraft resources than GUVI required. And then finally, we are also expecting that GUVITO will cost less than GUVI based on the benefit from the heritage of the GUVI instrument and what's gone before. Thank you.